So hi, and in this video, I just want to conclude the discussion on first order circuits. And after this video, maybe after 1 or 2 days, I want to start revising the second order circuits. So I just want to finish off some of the pending things that I have kept since the previous videos. So let me just discuss one of those circuits. And here, basically, we had 0, 1. This is a step input to a circuit of this sort. And this is the circuit, if we recall. And here, the way that we were basically observing the output was like this, as far as I recall. So at high frequency, it will be positive, and low frequency, this will and at low frequency. So high frequency, this will come into picture, and low frequency. So I think I should the sign convention was like this. Yeah. And one can easily deduce that when all the capacitances are equal and all the resistances are equal, the output can just be determined on the basis of the initial condition and the final condition alone, and it will look something like this. We already discussed this before, right? But now, at that time, I just said that this transfer function derivation will take some time. But actually, I was wrong at that time. Maybe I was just exhausted. But we should realize that this transfer function can be derived just as quickly and easily as we did among did other things. The idea here is that let us first just try to find the zero of this circuit. Okay, so we know that when the zero of the circuit will exist, this node voltage and this node voltage must be equal, right? Which basically means that the response of this circuit, if you can visualize, this is nothing but a high pass system, and this is nothing but a low pass system. So this basically just means that the difference of the low pass and the high pass system must be zero. So we can just easily establish that uh, it can just easily be expressed by 1 divided by SRC minus SRC 1 plus SRC, right? And when this is equals to 0, that is when this V naught will be 0. And this, using this condition, we can find the zero frequency, which, as is also obvious from this initial condition, since it opposes the direction of the input, that we'll get a RHP 0. And thus, in this transfer function, the numerator is 1 minus SRC. Now, again, we understand that since the pole is needed to be found, we can just again use the same standard method, that we can just short this guy. And what we'll realize is it is RC in parallel, and this RC will be in parallel to the entire network. So basically, it is just three parallel RCs in series. So if we solve that, we can just easily establish that network will also just yield the pole of 1 plus SRC. And since we know the entire transfer function will be of this form, so what is this h of 0? It is 1 by 3, as we already know. So this is just the entire transfer function which we can just derive very quickly. And there was nothing big about this. And again, we can understand that this RHP pole came into picture because because basically the low pass response, we subtracted from it the high pass response. Yeah. So this is how we can easily find the transfer function of this particular circuit. Let us move on to another discussion that I wanted to do was of a simple high pass system. We are observing the output here, and here I have fed some input CR. So we know that this transfer function of this circuit is given by SRC 1 plus SRC. Yeah. Now we know already that for a low pass system, the impulse response will be given by what? 1 by tau E minus T by tau ut. And now, since this is basically akin to S times tau, so this means that if I just want to find the high pass response of a system, I can just simply take its derivative. And so what I'll get is this guy, this guy, uh, minus e minus t by tau by tau square ut. Yeah, this is the derivative. But we know that there is a tau also multiplied over here. So this tau will be multiplied here and here. And so this is the expression that I'll be observing. Cool. Now that I have this expression, so we can easily say that we can obtain the high pass response by just simple differentiation. Another clever way of finding it is just that you subtract uh, from and the all pass response, the low pass response. So we know that the all pass response to a impulse input will obviously be the impulse, and the low pass response was this 1 by tau e minus t by tau ut, and so still we can easily tell that we'll get the same result, right? So these are two ways by which we can just use our existing low pass system knowledge to basically predict what will be the high pass response. But that is not the point here. What I wanted to basically answer here, or what I basically want to explore here, is that we can tell all of this by intuition, yes, but is there a way that we can intuitively comment upon why this response specifically looks like this? So the response, how this response looks like is that there is an impulse at zero, and then there is a decaying exponential in the opposite direction. So this is what I actually intend to answer, is that what is exactly happening over here. Okay, so physically, what is happening in the circuit is the moment we feed an impulse, this capacitor won't allow sudden change of voltage across it. And we can see that since this capacitor won't allow sudden change of voltage across it, so if this is impulse, this will also then be impulse. Or alternatively, this capacitor will allow a high frequency change, and at output, we'll see an impulse, as we can see from this portion of the output. After this t equals to 0 time has elapsed, what will happen is that now we must understand that this capacitor will get shorted because output is now 0. And this is the scenario we will be posed with. Yeah. Now, what we must understand is that since an impulse voltage, since an impulse appeared across the resistor, this implies that what current flowed through the circuit was impulse by our current actually flowed through this capacitor. Because of this current flowing, there was some charge that accumulated in this capacitor. Since this is the current, the integral of this current divided by C will give us what? It will give us the it will give us integral of this current basically will give us the charge that this capacitor accumulated. And since it is for t equals to 0 time only, so we know that integral of this guy is a unit step, right? And the unit step at 0 is equals to 1. So we can understand from this is that 1 by r value of charge got stored on the plate of this capacitor, which will be in like this, right? Plus minus. Now, since this plate is grounded and this capacitor effectively has 1 by R charge, so we can from this infer that the voltage at this node will then be negative, right? So basically 1 by R charge is stored across the plate of this capacitor initially. And so, what will be the value of the voltage across the capacitor? That will be simply minus 1 by R divided by C, which is 1 by tau, which we can understand comes from this term. So we know that if we substitute 0 here, it is 1 by tau, right? This is what we can see, it's 1 by tau. And eventually, this voltage will then decay across, will this negative charge will basically try to decay out, right? So basically, this negative charge will decay through this resistor, and alternatively, we'll feel as if some positive current is flowing eventually till the time this voltage across the capacitor dies out to 0. So this is the physical intuition behind this, that since this capacitor passed some impulse voltage across it, it stored some charge, and this charge basically was the reason why we are having this negative exponential. So this was the physical explanation behind what was happening in this high pass circuit, and why are we typically observing such kind of a graph. So that was the physical picture, and I think this physical picture was important to discuss because many times this physical picture only will save us in basically commenting intuitively in circuits whether we observe some impulse in the scenario or not. That being said, one of the final things that I want to pose is that let us consider that we have this circuit. We have a current source. I have a switch which I open at t equals to 0 time, and I have an inductor connected across it. And this circuit is basically connected at t equals to 0 time to a inductor resistor circuit, which initially was carrying 0 current, right? So here I of minus 0 is 0, and here we know that I of minus 0 is 6. So the question here is that after the switch is closed, the circuit will look something like this, right? The question here that I'm trying to pose is that this inductor will not allow sudden change of current across it, and thus it will seem as if this inductor is still carrying 6 ampere current at t equals to 0 plus time. Alternatively, this inductor will force current of 0 across it because initially it was carrying no current, so it should force 0 current across it, right? Which implies that two things are possible. Number one possibility is that if I name this inductor A and I name this inductor B, so that means that inductor A will basically conserve the current across it for the switching instant, and the sudden change of current will happen across B. So B will allow sudden current change, and 6 ampere current will flow for t equals to 0 plus time. Alternatively, we can say that B will prevail and the current across A will die out instantly, and the initial value of current will also be 0. So the question here is that which of these two cases must happen? If you think about this intuitively, or if you try to think about this, what should happen physically, it doesn't really seem to make sense that the current flowing through the inductor will suddenly drop down to 0. But one may argue then that also does not make sense that the current which was initially 0 through inductor will arbitrarily rise to 6. So this is a question that if someone is watching this video, I'd urge you to think on this. And even I'm personally thinking on this when I fed this to AI. AI said that uh, neither of the cases are possible, and this circuit itself is not a possibility. And basically, in reality, some wire resistances will come into play. Some wire resistances will come into play. Some wire parasitics will come into play, which will not allow such kind of a dilemma to come into picture to begin with. But still, I'll encourage someone who's watching this video to think on this. So these were the concluding things I wanted to discuss about first order circuits. Again, as a reminder that if someone is watching that we should just also remember the mathematical foundations of differential circuits about complementary integral, particular integral, because these would help us in solving more and more complex circuits even more in a more quick fashion in certain cases, and because these differential solutions will help us to comment on transients more effectively. So that being said, I think this finishes our discussion on first order circuits, and from the next video onwards, we'll be revising the second order circuits and op amp circuits, some basic op amp circuits, basically where we treat op amp as a block, and maybe some basics of network theory. So that's all. And if anyone is watching, thanks for watching, and I'll see you in the next video.